Hello, can you see my PowerPoint now?
Yes.
Can you see my screen now?
Yes, yes.
Okay, I will start. Hello, everyone. I'm Chao Wang from Changshu Institute of Technology. Here, I'm going to introduce a production plan study with Trump, a famous bending machine manufacturer. This study established a mathematical model based on the real working environment and compares two kinds of these algorithms. First, I'm going to introduce the background, then about the mathematical modeling, and the algorithm part. Finally, is a short conclusion. This study starts from last December, cooperated with the factory of China. As seen from the follow sheet, the bending process plays a vital role in the whole production. It was a bottleneck process and needed to be promoted. The objective of this study was to find an algorithm helps to production plan. Difficulties existed in the mathematical modeling and an appropriate algorithm to solve the optimization problem, which have huge amount of combinations. In the bending process, these flexible manufacturing plants have 4 different bending machines, and you can see they have a different series number. So they have different capability. The current production plan was assigned manually. Then they put them into the math system. So many problems were brought in with this traditional operation procedure. As seen from the moment analysis, processing and die changing occupies more than 60% of the total working time. The fine manipulation and the preparing time could also be decreased with appropriate scheduling. The data used in this study comes from real 1 day's production data. And on that day, only 55% of the tasks at one machine were finished. In order to increase the production capacity, our purpose was using this algorithm to have a more smarter production plan. In the future, we also plan to help the flexible manufacturing factory like Trump could use this intelligent production scheduling method in their math system. In this study, the mathematical modeling was tough to establish. Many conditions were significant enough to be concerned. As the plant have different kinds of machines, a variety of work pieces faces machine selection problem. Depends on the machine type, processing time, and the limitation of 450 minutes working time per day. Also, the number of work pieces is less and more varied. They require different die, including upper die and lower die. And this considering the die change time, and with considering plenty of time could be saved. As the work pieces were assigned to 4 machines, we focus on the machine with the longest working time, including processing time and die change time. For the die change time, it was determined by the die of the previous and the current work pieces with rulers. In the mathematical modeling, many assumptions were made corresponding to the real situation, and you can find more assumptions and their details. We are going to put them into the coming chapter. Here was the method for work pieces to select the feasible processing machine. It depends on the bending force and the length. The calculation of bending force was same as the current database of Trump factory. 2 different bees algorithms were performed in this study. The first one comes from the basic bees algorithm. Elite sites and base sites carry out the local searching with different number of bees. Due to the large number of combinations, the solution was very unstable. With Professor Pham's advice, we tried the second kind of bees algorithm with the site abandonment technology. As seen from the figure, each iteration will abandon some sites with good performance and give more attempt times for those with better performance. At the same time, the sites with more attempt times will shrink their searching radius. At there, we also found the number of attempt times for great sites was hard to confirm, as new sites were hard to come inside, as their solutions was better than the sites after many attempts, although they may have potential faster solution. In the code, we made a matrix to unite the machine selection and the operation selection. In the middle figure, when machine 1 is feasible, 0 updates to 1. So you can see here 0, 0, 3, 0, 2, 3, 5, 2, 3, 4, which means these work pieces could assign to machine 2, 3, 4, not the machine 1. In the machine selection stage, we use the router and the random to have new solutions. In the operation sequence, the work pieces assigned to the machine were sorted by the rulers, which we mentioned above. After decoding, we can have the solution like this. 2 and 4 means the workpiece was processed by machine 4, and its operation sequence was 2. In the machine mutation, the BA with site abandonment technology, we have an initial mutation probability of 15%. During each iteration, these local searching radius would be decreased, and the minimum mutation probability was 5%. For the operation sequence mutation, we also do some limited exchange based on the rulers. For the initial site and the elite site, abandon mechanism. Oh, sorry, I lose one page. Maybe. For the initial site and the elite site abandonment mechanism was different. For initial site, if the agreement after several local searching less than a certain value, these initial sites would be abandoned. For the elite site, a certain number of attempts was given, and each attempt shrink the local searching radius. After the stagnation reached a certain number, the site would be abandoned. This figure was the result of BA without site abandonment. The results come from the machine 2, which have the longest working time. It could be observed that when the number of iterations was 24, a relatively poor solution was retained for some time. This figure was the result of BA with site abandonment. Comparative stable solutions were evident when the number of iterations was around 36. After comparing two canned BA algorithm, 469.5 minutes was obtained as a result in this study. This result comes from many boundaries respect to the real working condition of the flexible manufacturing plant. The plant could benefit from this study not only the optimization, but also the rules we set for the operation sequence and other workers to help them reduce manual work. That's all my report today. And if you have interest in this study, you can contact me with the below email address. Thank you, everyone.
Dear Professor Pham, the workshop chair, committee members, and organizers of this international workshop on the BIS algorithm and its application, thank you for this invitation and the opportunity to meet old friends and new friends from all over the world. I am Dr. Ang Mei Chu from University Kebangsaan, Malaysia, and my co-author is Dr. Ng Kok Weng from University of Nottingham, Malaysia. The title of our proposed chapter is Minimizing Printed Circuit Board Assembly Time Using BIS Algorithm with TRIZ-Inspired Operators. This presentation will cover topics on introduction and problem statement, PCB assembly system with MBTD characteristic, theory of inventive problem solving, TRIZ-Inspired Operators, the implementation and results. PCB are used extensively in many products, such as computers, mobile phones, electronic tools, and controllers. A PCB may contain different parts with different shapes and sizes. PCB assembly is the process of placing these electronic parts or components, such as resistors, capacitors, transistors, on a PCB board, and usually it is a time-consuming process. Thus, PCB assembly needs to be optimized such that the sequence of component placement can minimize the total manufacturing time. In this work, we will focus on PCB assembly system with MBTD characteristic. PCB assembly system with the moving board with time delay, MBTD configuration, is the most complex assembly machine. This is because it requires the synchronization of three mechanisms in the assembly: the feeder system, the multi-head direct pick-and-place system, and the XY assembly table. During assembly, these mechanisms move at the same time. The synchronization involves complex coordination of the feeder movement from one point to another to provide the correct component for the multi-head direct system. The XY table that moves to the placement position, and the multi-head direct that rotates to a position to pick up a component and place another component at correct placement position at the same time. The three important times to be considered are the traveling time of the XY table, the traveling time of the feeder carrier, and the direct indexing time. Among the three timing, the longest of the three is the time needed in the assembly of each component. The movement of the two faster parts among the feeder carrier, the XY assembly table, and the turret need to wait until the slowest movement has been completed. TRIZ is an abbreviation from Russian language. The translation is the theory of inventive problem solving. It is created by Garrick Asrul, a Russian engineer who studied inventions from many resources, including patents. He looked for any similarity between different inventions. Asrul found out that there are 40 inventive principles, and most inventions follow at least one of the 40 inventive principles. In other words, these 40 inventive principles can be used to boost our creativity. We have used only 3 inventive principles from the 40 inventive principles to create the TRIZ-Inspired Operators. Not all 40 inventive principles were used. There are 3 inventive principles being used in the TRIZ-Inspired Operators, and they are dynamization, segmentation, and local quality. Dynamization is to allow the characteristics of an object, the external environment, or a process to change to find an optimal operating condition. If allowing the characteristics to change means it is making the object, external environment, or process to be more flexible, movable, or adaptive. Segmentation is about to divide an object into independent parts or groups. Local quality is about making each part of an object fulfill a different or complementary useful function. Dynamization operator is an operator that performs a change of group size. In the implementation, the group size is randomly altered in the new iteration if no improved best solution found in previous iteration. Segmentation operator divides the component representation and feeder representation into smaller groups. The group size may be different if the representation is not fully divisible, as shown in the diagram. If the representation has 12 components, the group size is 2, then we have equal size segments. But if the group size is 7, the first group is size 7, And the second group is the remaining of the 12 components, and thus the size of the remaining segment is 5. Local quality operator performs local evaluation in 2 modes: the intra-group mode within segment and inter-group mode between segments by using component sequence as illustrations in this slide. During intra-group, this operator rearranges the sequence of the component within group. If the new arrangement improves the total path distance, the new arrangement will be accepted. During intergroup, segments of components are rearranged to produce a new path. If the total distance resulted from this local quality operator is shorter than the initial path, the new path will be accepted. For the representation, each B will have 2 link representations to record the component placement sequence and feeder arrangement as shown here. In this work, N is 50 for 50 components and R is 10 for 10 feeder slots. The TRIZ-Inspired operators are applied separately to the 2 representations for component placement sequence and feeder arrangement. Next to it is a flowchart to show where TRIZ-Inspired operators were positioned in the BIS algorithm. This is the result of the implementation. We have obtained 23.42 seconds. This is the graph that shows the component pickup sequence that helped produce the minimum time of 23.42 seconds. This is a comparison table. Assembly times from several references are listed for comparisons. As you can see, the TRIZ-Inspired operators have provided the most desired timing for this assembly problem. Conclusions: TRIZ-Inspired operators have helped to find the optimal timing. They have met the ultimate requirement of the problem, that is to minimize the PCB assembly time. Although it is a very small improvement, but due to large production volumes of PCB assembly in electronic industries, a minor reduction in cycle time will actually save significant production time. With that conclusion, I would like to end my presentation. I hope you found it useful. Thank you for your time and attention.
That is mine. So let me please share my screen. Mine will be a live presentation. So please wait 1 second to share my screen. Presentation. Okay. Okay, I think you should be able to see my presentation now. So I can start. Okay, my presentation, my work is entitled Text Optimization using the BIS algorithm in a modern cloud remanufacturing system, and was developed with my colleagues of the University of Campania, Professor Fera and Professor Macchiaroli, and with collaboration also of Professor Pham. The objective of my research is the application of the BIS algorithm in a modern remanufacturing model based on cloud technologies, which aims at pursuing sustainability and circular economy principles. The presentation will be organized as follows. Firstly, the remanufacturing as a driver for sustainability and circular economy will be introduced. Then the importance of using cloud technologies also in manufacturing will be highlighted, and the cloud remanufacturing model will be described. Finally, we will use the BIS algorithm to test the scheduling phase of the model, and results will be evaluated. So the British standard defines remanufacturing as the series of steps needed to transform an old product into one that can be considered as new, having at least the same performance and the same warranty of a new product. From this definition, it is clear that remanufacturing process perfectly fits circular economy principles that aims at erasing the concept of end of life for products. And also, two sustainability pillars are achieved, the environmental, the economic one, since remanufacturing allows to avoid new production and ensures an economic growth by preserving natural and social wealth. Today, we are in the era of Industry 4.0, which is leading to the development of new technologies. Cloud technologies are among the most important, aiming at transforming resources and capabilities into services which can be shared all across the world and can be remotely managed in an intelligent and unified way. Usually, the cloud structures have three types of users. The cloud service providers, who are the ones who share their resources and capabilities in order to have profits. The cloud service customers, who are the one who requests for the use on demand of such resources and capabilities by paying a fee. And the cloud service brokers, who are the managers of the cloud platform, managing also the interactions between the providers and customers. The introduction of cloud technologies in manufacturing is not actually new. In fact, it was introduced by Lee in 2012 with the concept of cloud manufacturing. And relying on that, we developed our cloud remanufacturing model. In this slide, the framework of the model is shown. It is mainly divided into two parts. The first one concerns the management of requests by the customers and the scheduling process. The second one concerns the management of the real remanufacturing process. In order to realize a model like cloud remanufacturing, some important features are needed. For example, technologies like cloud computing to create a service-oriented architecture, or tool for resource virtualization, or Internet of Things in order to have real-time data on the resource are needed, and as well as cybersecurity system that should be implemented in order to guarantee the data security of providers and customers. Also, the correct address, also some information about the product, like the materials used, the assembly and disassembly data, or other technical data, should be correctly addressed after the scheduling process in order to avoid an information overload to the providers. Obviously, the main objective of customers concern times and cost minimization when they want to remanufacture their products. So the model must take into account these aspects. In this slide, for example, we define the total time for completing the remanufacturing process in a cloud remanufacturing environment. And it depends mainly from the activity completion time that is made by a processing time, a logistic time, and a waiting time. The waiting time is the time a job has to wait because a resource can be busy with other jobs, while the logistic time is also very important in a model like cloud remanufacturing, since transportations may be needed to transfer cores or components from one provider to another. So following the same line of reasoning, we also developed the relationships for determining the total cost for remanufacturing process. In this context, we want to analyze the make-span optimization problem in the cloud remanufacturing. The make-span optimization problem consists in assigning and scheduling activities having as objective the minimization of the total time for completing the process. So in the hypothesis that each resource can perform only one activity at a time, an activity can be carried out by several resources, but it can only be processed by one. And once an activity is started, it cannot be interrupted until the end. We developed the mathematical functions, the objecting function, and the related constraints of the model. And we used the BIS algorithm for a test case concerning the maintenance phase, the maintenance macro phase of the remanufacturing process, which in our case study is made by 26 activities that can be assigned, scheduled to 30 different cloud service providers. We used a full factorial plan of experiments to test the BIS algorithm with different parameters. In particular, we used only two levels, a low level and high level, for a total of 32 experiments. Each experiment has been run for 10 times, and we also had the two different levels of iterations that are 100 and 200. So here they are the results. In this slide, we can see the influence of the number of scout bees. With the blue line, we will represent always the low level parameter. With the orange line, the high level. And as we can see, when passing from 20 to 50 scout bees, there is a great improvement in the average results reached. The average improvement, in fact, is greater than 13% for both cases, for both iterations cases, even if, as you can see, the computational time also is greatly affected as it increases as well. This is the influence of the number of best or selected sites as that is expressed as a percentage of the number of scout bees. You can see when passing from a low level to a high level, there is not a great improvement in the average results. The average improvement is 2% in both iterations cases. And this is also true when we watch at number of elite sites. When we pass from a low level to a high level, there is an improvement in the average results less than 3%. So highlighting the fact that exploration seems to be not very effective in this case, but maybe it is only because we set very low parameters for the number of scout, for the number of elite sites and best sites. When looking at the plots instead of the influence of the number of best bees, we can see that when passing from a low level to a high level, there is a good improvement, greater to 6% for both iterations cases. And this is also true when we look at the number of elite bees, reaching an average improvement greater than 9% when passing from the low level elite bees to the high level. So in conclusion, in this paper, we defined the cloud remanufacturing model and used the BIS algorithm to test the scheduling phase, the basic BIS algorithm to test the scheduling phase of the model. Results highlighted the importance of increasing the number of scout bees, while increasing the number of sites for local search seems to not greatly affect the average solutions. A good exploitation instead of the elite and best sites allows to reach better performance in this type of model. For future works, we would like to increase the number of levels of the design of experiment, and also to propose a sensitivity analysis for determining the best BIS algorithm parameters in cloud remanufacturing scheduling. Okay, thank you for your attention.
Mario, thank you so much, Professor Pham, for organizing this event. Maybe this, like you say, second event, but the first one that was virtual event. Mario, thank you for organizing and for hosting this interesting section. You are one of my co-authors of the paper. My paper is about the clustered BIS algorithm for the advanced scheduling of in additive manufacturing context. It was realized in cooperation between 3 universities. The first one was University of Basilicata. I came from Italy, and my university is situated in the south part of Italy, in the middle between Sud and West Coast. It's just some marketing opportunity. But there are other 2 universities, Second University of Napoli, where colleague Mario and Marcello Fera came from, and University of Salerno, where Professor Lambiase is coming from. What about the context of this presentation? As I suppose all the people in this room are really experts in the application of this algorithm, I will try to focus on the context of analysis. The major part of this presentation is about additive manufacturing perspective. So the first part of the presentation will explain you the context, additive manufacturing, and will explain the motivation of the work. Then I will present the approach that is generally divided in 3 parts. The first one is related with the customer requirement, the second one is related to the product requirement, and the third one is related to the process requirement. And finally, I will present just a slide of a result with comparison between the application of this algorithm, or maybe a modified this algorithm with other implemented approach. Just to make you a note, I will not present you the data of my context, because the data were published in some paper, and if you are interested, you can have the title of the paper where the data came from. Just to be in the field of analysis, what I am talking about. We are talking about shadowing. Okay, maybe this form of shadowing was in the form of single machine shadowing, but in particular we are talking about shadowing in context of additive manufacturing. Additive manufacturing is a kind of a new process. I think that each of you know what additive is. It is a new process where the material is added. And the problem of additive manufacturing is generally related with how can I decide the product to be included inside the chamber of the additive manufacturing. So I found it that this shadowing problem will be divided in 3 parts. The first one is related with the nesting problem. Generally, in the state of art, deals with the nesting like separate problem in shadowing. The second problem is related to how the nesting could be fit inside additive manufacturing scenario. And obviously, there is also another problem that is related with the sequence of jobs, so maybe the sequence of build in relation to the customer order. I try to have the utmost synthesis in this slide, because this is the concept core. We started with the analysis investigated the clustering approach and maybe the constraint to implement clusters. Okay, so it means that in this part of the problem we will be focusing in the relation between part and build. Then I will try to fix the problem between cost analysis, so the relation between additive manufacturing and shadowing, and finally the relation between demand and shadowing part. Just to say why we decided to focus it inside additive. Additive is maybe one of the pillars of the industry 4.0. It is a kind of technology for technology revolution. Okay, today we are thinking to the industry 5.0, but additive is one of the pillars of 4. From my perspective, I am not a technology engineer, but I am a mechanical engineer. From my perspective, that I am an industrial engineer currently working like industrial and teaching like industrial. The additive manufacturing is a kind of revolution in the field of supply chain, maybe, or life cycle assessment, because we are thinking at a project that could be able to reduce the steps from the idea to the end user. In the past, additive manufacturing was considered like a prototyping tool. Today, it would be applied for example, in the previous presentation, Mario explained, can be applied in the field of spare part management and maybe maintenance and repair, or in the field of rapid manufacturing. There is a great concept today about the application of additive manufacturing. This is just a slide to explain how we thought at additive in the past, and how we are thinking to additive. Currently, additive is applied in the field of jigging, fixture, and tooling because it's able to reduce the time to market. There are different types of process. In particular, during this project, I will focus on a particular type of additive system. Is a power by fusion system. Inside the class of power by fusion system, there are more than other processes. Okay, and we thought that additive manufacturing was one of the applications that can help us to reduce the life cycle impact. There are just few screenshots about how the supply can be reduced or the life cycle can be assessed. So we think that additive can help in the field of life cycle assessment and maybe in the field of circular economy. We implemented some publication, or we analyzed some publication about this main topic. So going inside the problem, how I fix my problem. My problem was fixed with two objective functions. I will start from that. The first one was relating to the shadowing perspective, and in particular, the first step, FET, means that I will select the type of job that I need to perform, or the type of build, in this case, that I need to perform according to the customer's requirement. And generally, the customer's requirements are about when I want that the job need to be in the house of the client. So we fixed the first part about scheduling according to the principle of tardiness in nearness, because we are thinking at the project that is working in a just-in-time approach. We need to complete the job when the client wants the job to be completed. So there are some constraints and there are some data. The data are about the type of material that I need to perform, the amount of product that I need to realize, and the due date that the customer is asking me to respect. And I want to complete exactly when the due date occurs. The second job is about optimization of the process, or the second objective function is about optimization of the process. In this case, we focused on the type of process that we perform, the type of material that we are working. We focused on the setup cost, or maybe the setup time that we need to arrange, and maybe how much volume inside the chamber of production is occupied, because that problem is about removal cost. So there are some constraints about type of process type of parameter inside process, that means the amount of time, part quantity in this time that can be included inside the chamber. In our approach to the problem, the decision function was weighted with some amount, because we want to implement something that the decisor can change. There are different constraints. Maybe the constraint is about the product is about dimensionality of the product, but can be also about the form of the product. So if it can be rotated, or if it cannot be rotated, and if there is a kind of predominant dimension, because this step is more in the field of nesting, or maybe clustering. We analyze the problem in the field of banded volume optimization. Here there are some just examples, and there are also two publications that contains the data that I implemented, also the comparison, the comparison algorithm that I decided to check. I will be fast because there are just 9 minutes. We selected 3 types of material: titanium, aluminum, and stainless steel. We chose 3 types of material. We implemented the budget build, and we evaluated how the volume can be respected according to some nesting perspective. The step of nesting was elaborated with 2 steps. The first step was a deconstruction phase, and the second step was a construction phase. The construction phase was realized when we understood that the volume of chamber was not respected. So we extracted the first time the job, the build randomly for the chamber, and we deleted some part inside the job in order to respect the total volume constraints. In the construction phase, we had some part in the chamber. In order to implement this nesting perspective, we implemented the BIS algorithm like a separate approach to construct the build for the exploration. And in order to improve the exploitation, we included some taboo rules between the selection part. After the first part, it was about nesting. We decided to implement the scheduling, and we approached the problem like the case of a single machine, earnest toughness penalty problem with the added of the cost amount. Here, as I tested this algorithm and a modification of this algorithm, I am presenting you the modification version. It's about I call it the genetic BIS algorithm. It's a kind of BIS algorithm that is going to implement a super BIS able to rewrite the recombination mutation and some other genetic function. I call it the part in which the genetic amount was implemented like the jumping function. And here is just a description how the algorithm works, because in the first part there is the tradition of this algorithm, but in the selection part, when we noticed that there is a stack in a local optimum, we implemented the jumping function that moves from crossover mutation and random mutation. Maybe this part can be timely checked in order to show you the difference between these and genetic BIS algorithm. There are two graphs in the left side that will explain you like the genetic BIS algorithm. We explore the domain better than the BIS. We applied the genetic BIS algorithm in the context of analysis, and we made comparison between poor genetic, taboo search, BIS, and genetic BIS. Here there are just some results relating to the data that you can check inside the paper. We found that the service level, we measured the service levels like the amount of clients that were satisfied in relation to the total order that we received. It was nearly to the 93%, so higher than the other approach. And we also evaluated the genetic BIS algorithm according to the total cost from the starting solution to the final solution, and we got the best performances at the moment. Our intent is to evaluate if we can improve the genetic BIS algorithm while tuning appropriately the algorithm. So just to conclude, I think that I was really late. My conclusion is about the context of analysis. So a lot of people say that additive manufacturing currently is not a mature manufacturing technology. And it's not measured, and it cannot be compared in terms of cost with other type of technology like the subtracting one. We thought that the comparison can be done when complex shapes can be performed, but comparison can be effective, can be cost effective, even though we are evaluating the total life cycle cost of the project, because additive manufacturing will help us to reduce the step inside the supplying, and can help us to reduce the recycling. For this reason, we investigated the scheduling process inside Additive to consider a single machine problem. We found that sometimes the BIS algorithm, if not properly tuned, will stock in local optimum. We improved the BIS algorithm with a genetic jumping function, and we found that in some context of analysis, we can get at the moment the optimal performances. Thank you so much. If you have any questions, you can be free, I think, to write in chat or to explain. Thank you so much.
Thank you.
Hi, my name is Asrul Ismail. Today, I'd like to share our most recent work on the B's algorithms titled the B's traplining metaphor for vehicle routing problems using decomposition approach. According to Zhou in 2002, the meta-heuristics are the most promising and effective methods for solving a difficult combinatorial optimization problem. New users, on the other hand, may be confused by the preparation of the meta-heuristics, including B's algorithm, because of the massive initial parameters that have to be tuned. For basic B's algorithm, we will set 6 parameters, for standard 8 parameters, and for most cases, we'll add 1 or 2 more parameter setting for the stopping criteria. Can you imagine having to deal with 6 to 10 parameters prior to running the algorithm for the first time? So the purpose of this study is to apply a traplining metaphor to combinatorial B's algorithm in order to make the algorithm more simple, accurate, and faster. We use vehicle routing problem using decomposition as the case study. Traplining is the recursive movement pattern in which an animal returns to previously visited location is typical in the animal world. In 1979, Janssen coined the term traplining to describe bees visiting flowers in a repetitive manner. The terminology is derived from a comparison to human trapper who inspect their traps on a regular basis. We developed the B algorithm in the study using the concept of traplining as the main source of idea. In our most recent study, we reduced parameters using the traplining metaphor by observing bees exploring and exploiting a patch concurrently. By integrating these two processes, we can reduce parameters to as few as 2 parameters without jeopardizing the B's algorithm's performance. This concept will be applied to the combinatorial B's algorithm in this study. So, how can we reduce the parameter without jeopardizing the fundamental principle of foraging? Indeed, the ranking procedure in the B algorithm may provide us with critical information about the number of workers and the size of the search. The most visible site, which must be a rank 1 site, may have maximum number of workers assigned, and its size would be the small radius around the patch position, and vice versa. We can obtain additional site information by assuming only the number of patches or scout bees and the maximum worker bees that will be assigned to the elite site. If we use the linear relationship as shown on the graph, we can determine the number of the workers and search size from the second to the last rank, as we already know the maximum and minimum searching size and workers. In poor sites, the minimum worker population will be 0, requiring a re-exploration of searching space with the scout bee. As a result of this principle, all parameters that is required to run the B's algorithm are only n, the number of scout bee, and nep, the maximum number of worker bees. In this version, we use a triangular random number distribution to assign exploitation and exploration concurrently. As a result, each patch includes both exploitation and exploration by determining the likely value. For instance, if we implement the assignment on an elite site with 5 worker bees using triangular distribution with minimum value equal to 0, likely value equal to 0, and the maximum value equal to 100%, it would assign 80% of workers to search in the range of 0% to 60% of the solution space, while the remaining 20% would search more than 60% of the space. It will apply in reverse in the most poor location. The bee will be assigned with the task of searching for up to 100% of the available space. On the other hand, a recent study demonstrates that we can improve the accuracy and the speed of bees algorithm by observing the bees threat avoidance behavior. By adopting this behavior, the intensifier can reduce the error of the basic version by more than 5% and accelerate the convergence by at least 3 times. As previously stated, bees engage in traplining behavior while foraging for honey. They will visit between 10 and 30 flowers on each trip, return to the hive, and come back to the same patch until the resource is depleted. However, on a subsequent visit, the bees may choose not to revisit certain flowers for various reasons. To put it simply, they are avoiding the threat posed by resource depletion or an intruder. As a result, the second development is an intensifier based on this behavior. Unlike humans, bees are unable to anticipate all possible paths using Google Maps and other tools. They must rely on trial and error to develop their own experience. The bees concentrate on their previous experience, collecting distance data by dropping specific flowers. After getting experience, the bees will improve the remaining flowers by eliminating sharp turns, and after the condition is safe, the forgotten flowers will be reintroduced again. To construct the complete tour, the bees travel all the flowers on the habitual tour and will memorize the closest path to the forgotten flowers. The bees will then insert the forgotten flowers in the center of the closest path on the subsequent trip. This intensifier is fundamentally composed of 3 steps: removing some random nodes, optimizing the remaining subtours using TOOP, and reinserting the removed nodes using the nearest path principle. Originally developed as part of the standard combinatorial bees algorithm, this intensifier was associated with the abandonment strategy. Due to the fact that we are using the bi-combinatorial bees algorithm, a variant of a basic bees algorithm, the intensifier will be located after the local search operator. The problem that we are attempting to solve in this research is a VRP, vehicle routing problem. The VRP is a real-world combinatorial optimization problem. It is one of the most significant real-world applications of a TSP extension. The problem is complicated by the presence of multiple salesmen, commonly referred to as a vehicle, with a specific capacity. They travel from one or more depots to cities with specific demands and then return back to the depots. In this study, we propose bees traplining metaphor for solving the VRP using decomposition. We would compare it with other basic version of bee algorithms. And for the instance, ALA101 and ALB101 are taken from TSP-lib. The instance have 100 customers, 1 depot, and a number of uniform capacity vehicle. To solve VRP using the decomposition approach, the problem has to be decoupled into 2 subproblems: clustering and routing plan optimization. The clustered customer with no capacity violation would be solved by using bi-parameter BA, and the route within the cluster customer would be solved by using the bi-parameter combinatorial bees algorithm. The local search of this CBA is using the combination of swap, insert, and reverse with the bees routing optimizer as the intensifier. After setting the parameters on the next step initialization, we use bi-parameter bees algorithm with coverage principle to cluster the customer subjected to the vehicle capacity. This approach starts from the circular shape initial centroid. The circular shape centroids are formed from random radius of coverage and random starting point angle or theta. All witness value with these initial centroids then evaluated. This initial circular centroid is then replaced with a better centroid that has the lowest variance and a capacity violation of 0. The movement was accomplished through exploitation and exploration. As we can see on the figures, the small black O represent the cluster's initial centroid, while the large black O represent the cluster's final centroid. After receiving the initial solutions from the clustered customer, the algorithm ranked them all. The recruitment and assignment are determined by this rank. Then, using the triangular random distribution, a combination of searching process is conducted. Finally, the BRO intensifier strengthened the solution by temporarily removing nodes, optimizing the subtour, and reinserting the forgotten nodes. We verify the accuracy of our coding prior to interpreting the data. The output of the proposed algorithms is rechecked to ensure that it was correct and feasible. The validity of the data is determined by the number of nodes visited, the capacity of each vehicle, and the total demands of all customers. To evaluate the proposed algorithm's performance, we also perform a basic combinatorial Bayes algorithm with the same maximum number of evaluation, or NFE. All methods are evaluated using accuracy and the NFE. For each method, the error and NFE are calculated over 10 independent runs. The accuracy and NFE result obtained in the form of mean and standard deviation. By comparing the result, it is clear that the addition of the clustering initialization and intensifier mechanism significantly increased the accuracy of the final average solution by nearly 6%. Additionally, the bi-parameter version of the combinatorial BA demonstrates no significant difference from the basic version. It demonstrates that parameter reduction has no harmful effect on the algorithm's performance. As shown in the graph, the proposed version also improves the algorithm's convergence speed. On the ELA101 dataset, the proposed algorithm achieves a 10% error rate, more than 10 times faster than the basic version. While on the complex ELB101 dataset, the proposed algorithms achieves a 10% error rate, nearly 4 times faster than the Bayes basic version. So finally, we can conclude that the two-parameter version of the combinatorial BA performs similarly to the basic version. It supports the previous study that demonstrated that using the continuous version of the bi-parameter BA did not impair the BA performance. And also the intensifier has the potential to significantly boost the accuracy and speed of the combinatorial Bayes algorithm. I think that's all from us. Thank you very much for your attention and see you next workshop. Thank you.
Hi everyone, my name is Jay Lee, currently a research fellow working at Vehicle and Engine Technology Center. It is a great honor for me to be invited as a speaker to present our recent work. Today, my topic is Pedestrian-Aware Supervisory Control Systems Interactive Optimization of Hybrid Electric Vehicles via Fuzzy Adaptive Cost Map and Bayes Operators. So my presentation includes 7 parts, which are team profile, background, research objects, a proposed solution, experiment setup, result, and discussion. Conclusion will be at the end. Vehicle and Engine Technology Research Center is led by Professor Chongming Choo. He has 7 years of industrial experience with Jaguar Land Rover and Ford. Over 400 journal and conference publications in engine flow, combustion, emissions, transition, operation control, and hybrid electric powertrain development. He is also a fellow of SAE and IMACE. CASE-FAE team is the biggest research group in this center, which means connected and autonomous systems for electrified vehicles. It aims to improve and level up transport across the world by making everyday journeys greener, safer, more flexible, and more reliable. Let's back to the research. Due to the nature of the engine vehicle exhaust system, pedestrians may experience events where specific emissions concentration are high enough to cause their healthy effects. Electrified vehicles are increasingly being seen as a means of mitigating the pressing concern of traffic-related pollution. Since HEV energy management is a continuous optimization problem, the definition of cost functions is strongly related to the driving conditions. Considering the diversity of realistic driving scenario, dynamic cost functions may more precisely reflect the fitness of holistic objects. There is including car owner and involved pedestrians, but need to be more investigated. Hybrid propulsion system, which is supervised by the vehicle controller, compresses a gasoline engine and integrated starter generator, transmotor, and is powered by the combination of fuel and electricity. As shown in this figure, here we choose a transmotor, that is an electric motor with float state. The ICE drive and the transmotor's drives are combined by combining them in series, so their speeds are added. There can be decomposed via the operation of the clutch and the lock. Main parameters are summarized in Table 1. So in order to minimize pedestrian exposure to the vehicle emissions nearby and the fuel consumptions, the interactive optimization methodology is proposed for the development of the pedestrian-aware supervisory control systems, as illustrated in this figure. This optimization methodology we proposed combines a novel fuzzy adaptive cost map and the BEAS algorithm to optimize the power split control parameters. The designed procedures include 3 main phases. The first one is conducting the standardization and aggregation of cost maps of fuels, carbon monoxide, hydrocarbon, and the nitrogen oxide. And the number 2 is reasoning the relationship between the pedestrian density and the weights of the cost maps by using fuzzy satisfying approaches. The number 3 is optimizing power split control parameters via BA and the developed the fuzzy adaptive cost map. First, the standardization and aggregation for exhaust emissions and fuel cost maps of the ICE is launched in advance to achieving the self-adaptation to pedestrian density. This treatment combines multiple fuel and emission components into a single target for reducing computational burden from the several table lookup operations. Due to different scales of the fuel consumption and emissions map, standardization should be given by using the first equations. After the deviation of the standardized cost map, the weighting process is done by the following equation. The weighting factor K is usually a set of fixed value determined by the human expertise. So far, the optimization target is combined by introducing the fuzzy cost map as a last equation. So then, in order to empower the cost map with an ability to adapt to the density of pedestrians, the relationship between the pedestrian density and the weights of the cost maps need to be established in reason. So considering the imprecise nature of the decision maker's judgment, it is natural to assume that the human decision maker may have fuzzy or imprecise goals for each object function. Here, the fuzzy satisfying approaches is adopted to interpret the relationship between one input, the pedestrian density, and the four outputs, custom maps weights of the field, CO, HC, and NOx. The rule base is shown as the left-hand side, and finally, the BIS algorithm is used here, which is suitable for searching accurately narrow valleys and holes, and for highly multimodal functions, like such energy management problem. Right, experimental setup includes two main processes. One is real-world cycle collection, which is conducted at the Dublin City University. In addition to the general information, the real-time density information of pedestrian walking on the sidewalks can be effectively estimated by local signal from their mobile phone exchanged to the cell towers. The other one is bootstrap sampling method adopted for learning a sample expansion that choose random samples with replacement from the sample data to estimate confidence intervals for parameter of interest. Here we show some results. The figures we displayed here as a fuzzy adaptive cost map under the different pedestrian densities. As an increase of pedestrian density, the high efficient area of specific consumption is migrating. It is like a dripping process. Yeah. So table 2 summarizes performance comparison of study 3 optimization algorithm. In terms of the successful rate, by using this three population size and the 3 levels iterations, the BA performs entirely significant superiority for the interactivity optimization compared to the other two. This slides discuss economy and the robustness of Pedestrian-Aware supervisory control system using the proposed interactive optimization methodology. More importantly, for an aspect of avoid the pedestrian explore in near vehicle emissions, this vehicle system can reduce the total emissions of up to 40% compared to the two. One is equalization and another is CO first. This is attributed to self-regulate objective weights of fuels and exhaust emissions based on a real-time signal of a pedestrian density during the optimization process. Right, so at the end, the conclusion will be drawn from the investigation. So the first point is the developed fuzzy adaptive custom maps can activate the fixed weights of the sub-maps and enable the self-regulation of objective weights based on the pedestrian density. So number 2 is up to 40% mass of exhaust emissions can be reduced for the involved pedestrian with the help of proposed approach, compared to the only considered fuel consumptions in mapping treatment. So the last one is the modified BA for interactive optimization shows the ability to achieve the highest accessible rate, which exhibits superiority in control optimization of the plug-in hybrid electric vehicles compared to another baseline, genetic algorithm and particle swarm optimization. Well, thanks for your attention and hope you can enjoy this.
My name is Michael Pakinatha. I'm from Cardiff University. I will be presenting the work on the application of the BEES algorithm in the digital twin for optimizing the process parameters of wire EDM. I'd like to acknowledge my colleagues, Theo Harris Alexopoulos and Sebastian Square. The outline of my presentation is shown here. The aim of the work is to study the wire EDM process and its process parameters and how these process parameters can be optimized in order to achieve the maximum quality. In Industry 4.0, we use cyber world in order to capture what you have in your physical world and to emulate your machine in your physical world in the cyber world, so that all the improvements, all the scenarios can be run on the cyber world, on the virtual machine, without causing any interruption to your physical world. And the connectivity is provided by the Internet of Things. So the digital twin is a virtual model of your physical system. Data collected from sensors and IoTs can flow from the physical world to the cyber world, into the virtual machine. The digital twin will behave like a twin for your real system. And your virtual machine can be used to run different scenarios, to emulate your physical system, to make improvements, study the usage patterns, reliability, efficiency of your real system. So the focus of this study is on the wire EDM process, where you have a wire which is used to machine or cut through a workpiece. It's a conductive, electrically conductive workpiece, and you have a dielectric fluid which is used to submerge the workpiece. When current is passed through the wire, there will be sparks created, and the energy from that spark will erode and cut through the workpiece. And the process is shown here, where the current, when it's passed through the wire, there's a buildup of voltage, and that will cause the arc or the sparking to take place, and so there will be charging and discharging of the electrical field. The wire EDM process broken down into three areas. Here you have the optimizing of the process variables, which is the focus of this study. We will consider the surface roughness, which is to be kept as low as possible, and material removal rate, which is to be as maximum as much as possible. And then you have the width of cut, which is the kerf width. However, we will only focus on surface roughness and material removal rate. The wire EDM process will consist of three operations: a rough cutting operation, finishing operation, and surface finishing operation. In this study, we will consider the rough cutting operation, where you will have the material removal rate and the surface roughness will be the focus. Wire EDM process will also be monitored with the KPIs through temperature, surface roughness, material removal rate, and the combination of these KPIs, which is called the overall KPI. If the temperature is in the right range, you include set it to 1. If it is outside the range, set it to 0. Surface roughness can be a linear value. And if the machine is broken, you set it to 0. Generally, smaller the better. For material removal rate, again, a linear value. Best is maximum. and 0 if the machine is broken. The link between the input parameters of the process and the measured output, which is the surface roughness and the material removal rate. These are the equations which link or connect the 6 input variables to the measured output, and it depends on the material, workpiece material. If it is steel, okay, this equation has been generated by work done by data. And similarly, if the material is different for the workpiece, if it is aluminium, then the input parameters are shown here, 8 input parameters, and these are the equations. Okay, these inputs will have a valid range where the input parameters can be monitored. The Bayes algorithm used in this study is the standard Bayes algorithm, which uses local optimization and global optimization. There are 2 loops. In the first loop, the Bayes algorithm will be used to look at the objective function and optimize the inputs and outputs based on the workpiece material. And then using the found optimal inputs, the machine is run, and then the error is found between the theoretical value that you estimated and the current value. And then the Bayes algorithm is run again to re-optimize the process. So theoretical optimum is found using the first loop of the Bayes algorithm without taking into error the measured, without taking into account the measured errors. The second loop, the machine parameters are set to the theoretical values found, and then the error is compared with the baseline value, and the Bayes algorithm will optimize the inputs and outputs in order to find the best parameters. So I'm going to show you the results. There are 3 cases. The first case, the KPIs SR and MRR are equally weighted, and this is the range for SR and MRR. 10 random values are created, as you can see in the table. The theoretical optimum values are found based on the objective functions, and then you run the Bayes algorithm and you optimize the SR and MRR. And using those values, you find the error for the machine, and then you find the KPIs, SR and MRR, find the overall KPI. You run the Bayes algorithm again to find the improved or optimized overall KPI. So you can see that pre-optimization and the post-optimization, these are improved values. If you plot, you can see that the post-optimum, the red dots are always better than the blue dots. And the second scenario is where the SRR is favored more than MRR, and in this case we have 5 randomly generated values, and you can see the overall KPI is improved. And the third case is when, so the plotting the results, you can see the red dots are better. And the third case is MRR is favored more than SR, and again, only in one case, the overall KPI is slightly lower. Plotting that, you can see that although you cannot see the blue dots, they are overlapping. Okay, so in conclusion, the overall, the Bayes algorithm has improved the overall KPIs, except the one case I showed you. And when SR and MRR are equally valued, equally weighted, the improvement was 33.16%. So the study has shown that BA can be successfully used to optimize the input parameters for a real wire-EDM process. Okay. And for future work, more outputs can be considered, like kerf width and time for completion, and more cutting operations can be used as well. So thank you very much for listening, and these are my contact details. Thank you.